Rosen. Well, I know we're both behind you. Don't make no.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard. In our first example, we'll study something called Ballistic Pendulum. And we do this because in this process, both momentum and energy are conserved, but not at the same time. So we have a bullet coming in from the left at some velocity, and it hits the wooden target, is embedded in the wood, and then the piece of wood and the bullet, they swing together to some height. And this kind of device is in fact used for measuring the velocity of the projectile. But we would like to just calculate the height of this block, or how high does it swing to start with, and then we also compare the energies before and after the collision has happened. But first we have to analyze what happens when the bullet hits the piece of wood. So we see that they move together after the collision, so this is inelastic collision, and in fact completely inelastic collision. And in that case, energy is not conserved. Momentum is conserved, but no energy, because the energy of the bullet, it does some damage on the wood, and there are some friction forces as well that slow the bullet down, for example. So there's work done, and hence energy dissipated from the bullet wood system. Or mechanical energy is being dissipated and converted into thermal energy, like temperature, for example. But we can easily analyze what is the velocity of the block and the bullet after the collision, because momentum is conserved. So initially we only have the velocity of the bullet, mb vb, and that is transferred to the combination of the bullet and the wooden block, and that has some velocity, let's call it v2, and that's simple to solve. So v2 is mb over mb plus mw times velocity of the bullet, and we have some values here. The bullet is 12 grams, the wooden block 6 kilograms, and the velocity of the bullet 380 meters per second. So we put those in, 0.012 kg divided by the total mass, which is 6.012, and bullet velocity, and this gives for v2 0.76 meters per second. And then the second part, how high does it swing? In this case, the energy is conserved because we only have conservative forces working on this system, and that is the gravity. And because gravity is working on the system, it's an external force, momentum is not conserved while this swings up. So we cannot use that. But fortunately, the conservation of energy is enough to solve this problem. So initially, we only have the kinetic energy of the bullet and the wooden block, and they have the velocity v2 as we just calculated. And in fact, let's do this. Let's evaluate the amount of kinetic energy that we have after. So this is K2. So half times total mass 6.0112 kg times the velocity squared 0.76 meters per squared, and that is 1.67
joules. Let's keep that in mind. And by the conservation of energy, all this kinetic energy is converted into gravitational potential energy of the wood and the bullet. So total mass times g times the height y that we have here. And we can solve for y. So it's going to be K2 divided by total mass times acceleration of gravity. So 1.67 joules over 6.0112 kg and 9.81 meters per second squared. And that gives about 2.9 centimeters, or roughly 3 centimeters. And like I promised, let's compare the amounts of kinetic energy before and after the collision. So we have the value for after collision 1.67 joules. What about the kinetic energy before? And that's just the kinetic energy of the bullet. So half times mb times, that's m, times velocity of the bullet squared. So half times 0.012 kg times velocity squared, and that's 866 joules. So we see that only a small fraction of the kinetic energy is conserved for the pendulum to swing up. Most of it is dissipated in the wooden block when it deforms and warms up, and also the bullet will deform and warm up due to the interaction. So we see strikingly how in a completely inelastic collision like this, the energy is nowhere near to be conserved, but the momentum is. And that holds true for all collisions. Momentum will be conserved, but you have to be careful about the conservation of energy.
Hey, hey, hey.